Hello everyone, my name is Hui Chen from Chalmers University of Technology. I will present the progress of work package 3 of the 6G ISAC project, which focuses on the physical layer implications and enablers of distributed integrated sensing and communication. Here is the structure of the presentation. I will first give some background, such as work package 3 basics, objectives, and achievements so far. Then I will present the main results from the 3 tasks. Let's start with the work package 3 basics. Work package 3 has partners from CEA, Chalmers, Nokia, Orange, NKUA, MS, NEC, and Bosch. Consists of 3 main tasks. Task 3.1 on physical layer solutions and adaptive waveform shaping. Task 3.2 on sensing, localization, and tracking of active and passive objects. And Task 3.3 on sensing-aided communication. So far, we have delivered D3.1, the initial solutions, and it's preparing for D3.2 intermediate solutions, as well as our final deliverable, D3.3 final solutions, which will be due on month 36. This work package relates to 3 project level objectives: optimization of the physical layer, design of super-resolution distributed sensing techniques, and the design of sensing-aided wireless communication techniques. Work package 3 doesn't work in isolation. Our method and algorithm are constrained by the system requirement from work package 2, and they provide input to work package 4 for resource allocation and orchestration. The results are validated and evaluated in work package 5. So we are at the center, bridging theoretical enablers with system-level requirements and implementation feedback. So far, work package 3 has achieved in task 3.1 5 methods for optimization of physical layer parameters, waveform shaping, and deployment strategies for ISAC. In task 3.2, 15 algorithms for localization and tracking of both connected users and passive objects. In task 3.3, 3 sensing-aided communication schemes that leverage environmental awareness to improve performance. We also ensured those contributions tightly interacted with work package 4. Then let's move to some results. Before starting, let me briefly summarize the foundations of work package 3. We focus on positioning and radar-like sensing. Positioning determines location of a connected device, while sensing detects and estimates the change of the events in the environment. Then we integrated them into communication systems under the ISAC paradigm. They all require signal optimization and signal processing. We cover different forms of sensing, such as monostatic sensing, bistatic sensing, and multistatic sensing. We also deal with different synchronization potential and challenges, and on the different level of knowledge. Those forms can also be combined and related to various technologies. The process consists of 6 parts, from transmitter and receiver selection to information fusion and tracking, and all of them relying on the good ISAC channel models. Under the framework of distributed ISAC, we expect the benefits of spatial diversity, information redundancy, distributed processing and cooperative data sharing, and resource consumption. However, we should also deal with challenges such as synchronization, data management, and so on. Next, I will present some results of work package 3. To make this system work, one of the most important components is the channel modeling. Existing models include ray tracing-based, full-wave simulation, statistics channels, and EM-compliant models and measurements. And in this work, we use ray tracing models for theoretical analysis and algorithm design, while using measurements for validation and evaluation. Let's start with task 3.1 results. Task 3.1 investigates physical layer solutions and waveform shaping for ISAC. ISAC require optimized operation at both the sensing transmitters and sensing receivers. In this task, those aspects will be covered: the transmission, collection, and fusion of distributed sensing data, distributed sensing and localization operations, and simultaneous communication and sensing operation. Let me give you some examples. First, in our semantic aware waveform design, we tackled the problem of sending massive sensing data. In addition, we explored cooperative race-aided localization and on-site anchor beam calibration in a realistic multipath scenario. We also studied monostatic integrated sensing and communication and secure MIMO systems for eavesdroppers detection. Let's move to task 3.2, which is the largest activity in WorkPackage 3, focusing on algorithm for detecting, localizing, and tracking both connected users and passive objects. We developed 7 contributions for user localization and 8 contributions for passive object sensing and tracking. In joint race channel estimation and localization, we proposed a dictionary learning and compressed sensing framework that jointly estimate race channels and user location for robust millimeter wave localization. In frugal localization and synchronization, we designed a low-cost localization and synchronization method leveraging multiple races, requiring minimum infrastructure and computation. In phase-coherent distributed array, we introduced a distributed array approach where access points beamform coherently to enable joint localization and synchronization. In phase-coherent distributed array, we studied joint localization, synchronization, and mapping tasks. In near-field localization with dynamic metasurfaces, we explored terahertz band near-field localization using dynamic metasurface antennas, achieving high accuracy with controllable wavefronts. In mobile-aided users tracking, this work investigates user location and tracking by exploring mobile rays in combination with fixed beacons. Finally, we propose an opportunistic framework where available race configurations and the environment knowledge are reused for user localization without additional overhead. When moving to sensing passive objects, we use 5G standard signals in distributed architectures. We also introduced a cooperative method to detect blockages and locate UEs by exploiting interference from antenna side lobes. In race scanning for passive object detection, we leverage races to detect and cooperatively locate moving passive objects in the environment. We also studied large-scale long-term target tracking based on cooperative sensing nodes. And in distributed radar for multiple moving targets, we proposed a distributed radar system that jointly detects and localizes multiple moving targets by fusing raw radar data. In millimeter wave passive drone detection with rays, this study demonstrates how rays can enhance millimeter wave cellular systems to passively detect and localize drones. In RF imaging with physics-informed neural networks, we design an RF imaging approach that combines new physical models with physics-informed neural networks for improved scene reconstruction. In digital twin-aided sensing, we explore the use of digital twins for sensing with implementations openly available in the Siona library. Finally, we move to task 3.3. Task 3.3 investigates how sensing can enhance communication performance itself. We developed 3 main contributions: sensing-aided dynamic handover management, sensing-aided full-duplex communication, and sensing-aided beamforming and beam tracking. WorkPackage 3 also covers multiple implicit sensing-aided communication strategies, such as blockage prediction from dynamic objects, full-duplex radios for simultaneous operation, and so on. Here are some Task 3.3 contributions. In sensing-aided handover management, we propose to use predicted blocker position and directions, leading to much faster and more reliable handover decisions. In simultaneous near-field communication and sensing with full-duplex radios, we designed a terahertz full-duplex extreme large MIMO system that balances sum rate and 3D sensing accuracy with effective self-interference cancellation. In sensing-aided beamforming and beam tracking, we developed a Bayesian filter method with dynamic metasurface antennas to track 3D UE position in the near field. enabling accurate and adaptive beamforming. That's all my presentation. Thanks for watching, and please follow the project for updates and public deliverables.